This is a topics that I think it has a most subtopics as compared to other topics. Okay, so my main reference is control system engineering, Norman S. Nice. So you can refer to the books if you have any trouble understanding my lectures. All right, so next one. This is the CO2. We have covered CO1 in the previous class. The CO2 is the ability to perform system response analysis and stability in time domain. Okay, we will cover two types of systems. First order system, and then we will cover second order system. A higher order system, meaning that third order system, fourth order, fifth order, sixth order, and so on, will be also analyzed using the second order system that you will learn shortly. Okay, the first one is the first order system is a very simple one because you will have only plot something like this. Okay, remember last time you learned about the example of elevator. Okay, the elevator. So you will have the transient response and you have the steady state at the end of the response. Okay. Next one, this is a chapter learning outcomes. What you will learn in these topics is you will learn about the how to determine poles, how to determine zeros from the transfer function, and from these poles and from these zeros you can be you are able to determine the time response of the control systems. And then next is the describe the quantitatively the transfer response of the first order system. And next is you will learn how to write the general response of the second order system given the pole location as well as the zero location. And then after that, you need to find the damping ratio, natural frequency of the second order system. And then we will use the parameters for the second order system, such as cycling time, peak time, percent overshoot, rise time for the under them second order systems. And then next one is we finish learn about the second order system. We will try to analyze the higher order systems and system with zeros with the approximation to the second order system. Okay, the first one is to identify poles and zeros of the transfer function. So previously I have shown a few examples of the transfer function. The transfer function you can identify the numerator and denominator. So this numerator is called the zeros. S plus 2 over here is called zeros. S plus 5 over here is called poles of the transfer function. Okay, so numerator zeros, denominator is poles. So when we plot on the S-plane, so we have this S-plane, when we plot, we will represent the poles as the symbol X over here. Okay, symbol X, this is poles, and we have our zeros represented by the symbols of circle over here. Okay, y negative 5, y negative 2. So when you put it on the S-plane, so we have our zeros is S plus 2. So basically, when we put on the S-plane, S actually equals to 2. Okay? S equals to negative 2. The same goes for poles. We have S plus 5. So when you put it on the S-plane, it has S equals to negative 5. Okay, next one. So this is the, again, the same examples here. We have S plus 2, S over S plus 5. This is the system, GS. And let's say we have the input RS equals to 1 over S. So this is the step input 1 over S. So when we are trying to find the output, so remember the transfer function, we have GS So I don't want to use GS because it's a system is GS. So let's say our transfer function TS is equals to CS over RS. Okay, so the transfer function is CS over RS, output over input. So when we are trying to find the output, we can use CS over here. Basically, the CS is multiplication of RS to the system GS. So this is CS. So it is actually multiplication of RS and GS. Okay. So what we have is CS equals to RS GS. And we put in all the parameter or the system. RS is 1 over S. GS is S plus 2 over S plus 5. So you can find the response in time domain by the first one is you do the fraction here, the partial fraction. So you will find A over S plus B over S plus 5. So actually you have learned this in the previous lectures. So please refer to the previous lectures if you have any trouble understanding this. So from this, you can find the value of A, and then you can find the value of B. And finally, you take the inverse of Laplace transform. What you get is you get this form. Ct equals to 2 over 5 plus 3 over 5 exponential negative 5t. Basically, when we put in the S-plane, we can put it the input pole. Basically, when you plot it on the S-plane, so the input pole is actually 1 over S. Okay, 1 over S, meaning that the S location is at 0. Okay, the S is at 0. That's why you have this S located at the 0 position on the S plane. And for the system 0, you have negative 2. So you put it on the S plane, negative 2. So it is on the real axis. And for the system pole, you have 1 over S plus 5, which when you put it on the S plane, you represent it by the X symbol, negative 5 over here. Okay, so the output is when we represent it in the frequency domain or S domain, we have is CS equals to 2.5 S plus 3 over 5 S plus 5. And then from this, you can also represent the fraction like this. And when we find the time in the time domain, you will have the form of 2 over 5 plus 3 over 5 exponential negative 5t. This output time response, we can divide or we can classify the response into 2 types of response, which is the first one is forced response, and the second one is the natural response. Okay, the forced response is this. So the first one, okay, this is the forced response, and we have natural response, which is this one. Okay. All right. So the forced response is actually this one. Is contributed by the input. It is contributed by the input into the system. And for this natural response is actually the response that is due to the system itself. So in this case, what is our input? We have RS. What is our system? Our system is GS. The GS is actually when we calculate, what we get is 3/5 exponential negative 5t. And then the input is actually 2/5. There is no exponential in this expression. You can see here, this is a steady state response, meaning that the steady state response is when you plot it over t, what you get is the response, something like this. You have the first one is the transient response, and then you will get until time approaching infinity, you get the steady state response. So the steady state response is the value of steady state response is the forced response that is caused by the input. And then in between here, it is the transient response. So this transient response is caused by the system. Okay? The system you have here determine the transient response. So next one, I will show you the effects of poles on the real axis. So when you put it, we have the poles. For example, we have the first one we have at poles at -2. Sorry, this is actually -1. So poles at -1. So when you plot impulse, you know, impulse. This impulse is actually the let's say, so this is t, this is the amplitude. So you give impulse input. Impulse is just one. For example, so let's say the amplitude here is 1. Yeah, the amplitude here is 1. So you give 1 only at 1 second, and then you see what is the response of the input. You have the system G. Okay, you have the system G, and then you want to determine what is this the performance or the input, the output of the system due to impulse response. Okay? Due to the impulse response. So in this case, you have similarly you have CS equals to GS. Okay, RS. So now this input is impulse. So our GS now is 1/s plus 1. Okay, for the blue line. Okay, when you give impulse input to the system GS, which equals to 1/s plus 1, what happened is that it will decrease to 0. So you can see the blue line. It starts from at time equals to 0. So at time equals to 0, the amplitude is 1. So as the time approaching 5 seconds, 1, 2, 3, 4, 5, it decays and approaching 0. Why? When you find the time response of this output, so you will get this expression, which is A exponential -1t. A exponential -1t. So if you calculate using your calculator, exponential -t, you will get some value. You will get some value. So as you varies the value of t from 1, 2, 3, 4, 5, the value becomes lower and lower. The amplitude or the value of exponential -t become lower and lower. And when we have the other system, we have the system, now we have -5. Okay, we change our system to -5. What we have here is +5. So when we plot it, as we give the impulse response to the system 1/s plus 5, you will get the red line. You will get the red line. So the red line here, you can see the rate of decays, the rate of change of the amplitude becomes faster as compared to the system 1 over s plus 1. And if we have another one pulled at -10 over here, the rate of change, the rate of decays become much faster as compared to the previous pole as at -5. So we can give conclusion to this observation. We can say that as the poles is located to the left of the S-plane, so the rate of decays becomes faster, meaning it reach the value of 0 faster if we put the poles location towards the left side of the S-plane. This is a very important concept for you to understand. So the essence of this is that the poles that is located to the far left to the S-plane decays faster as compared to the poles that is located near the origin. Origin means 0, near the origin. So I give you last time test signals to the input signal, step function, the impulse function. Basically, we have test input signals that actually that I want to stress on this lecture is we have 3 types of test input signals that is important for you to understand. The first one is a step input. The second one is the ramp, and the third one is parabolic. Okay, so test input signal for this step. So this is the step. So this is the ramp, and this is the parabolic. Okay, parabolic. So this is how you should remember the test signals. Okay, so the step function is actually RT equals to A for t greater than 0. So meaning that 0, t less than 0. So if you extend the plot, it becomes something like this. So at 0, okay, it becomes A. Yeah, and then it's constant A, regardless of the time. For the ramp function, however, the function is RT equals to AT, which is t greater than 0, and 0 for t less than 0. So if you extend, something like this. And for the parabolic as well, AT square, which t for t greater than 0, and 0 for t less than 0. So something like this as well. So when you put it in S domain or frequency domain, you will have your step input is A over S, ramp is A over S square, and for the parabolic is 2A over S cube, S power of 3. So let's say we say that unity step, unity ramp, unity parabolic. So what you have is we have 1 over S square, 2 over S cube. So for the step input, it is normally been used to test the speed of a system that is subjected to abrupt change of input. Okay, we want to set, we have a system GS, and we want to see what will happen when we give step input. So this is we use to see this the response if you give step input. So we will get what will happen is that we have forced response and we have the natural response. So we want to see the natural response of the system, because the forced response is actually the final output due to the input test signal. So in this case, it's test. It's a step. And then for the RAM, normally we use to test a system to follow a linearly changing input reference. And for the parabolic, normally been used to test a system to follow a rapidly changing input reference. So we will see later in these examples the use of the test input signals. Basically, I have explained these test input signals in the YouTube. So please refer to the YouTube and try to understand how I make the test input signals using the MATLAB and relate it to the theory that we will learn later.